this video I want to show you guys a little bit about how to draw molecules out as far as their shapes go. That's what I mean when I say molecular geometry. Alright. Polarity we'll touch on right at the end. That's an extension of our geometry work, and we talked about polarity of bonds before. We're going to apply that to whole molecules. Alright. So, first of all, why we're doing this? Let's just ask ourselves a question. Why is molecular geometry important? Why are we even studying it? Well, we're studying it because it's part of the class, but also one of the big things that it's used for mainly is in drug design these days. A lot of drug design is based on things called SARs, which are structure-activity relationships. The way a lot of drug design is done is a protein's active site is determined. Let's say this is a protein, and it has a receptor that's got this particular shape. Let's say we've got a little lump sticking out here or something. Now, it's not somebody's mouth. This is actually a receptor on a protein. So if you want to turn that protein off, you want to make sure that you have a molecule that can fit in here. So it's got to have a particular shape. Now, of course, that's kind of a funky shape, but I'm just making this stuff up as I go. So we have this molecule that has this particular shape. Now, in order to design molecules with very particular shapes, you've got to have some idea about basics of molecular shapes. Can you design a molecule with that specific shape? Well, in order to do so, you've got to start somewhere. And the somewhere that we're going to talk about is very basics of drawing molecular geometries. All right. So when I say basic, we're talking about, say, methane, and carbon dioxide, and ammonia, and beryllium fluoride. You can see these are all very simple molecules with two types of elements. And there isn't going to be much in terms of possibilities that you can get here. We're going to have several different possibilities for what your molecule can look like. Essentially, you're going to have molecules that look straight. They're going to be linear. You're going to have some molecules that look what's called trigonal planar, where they are flat and in the shape of a triangle. That's where the name trigonal planar comes from. And then you have tetrahedral. Now, tetrahedral requires a little bit more detail here. You've got two bonds in the plane of the board. One coming out towards you is shown by this wedge, and one going away from you, which is very poorly represented by this dash. Hang on, let me erase that and start that bollocks again. So you've got, let me try that again. Bloody software. Alright, so you've got two groups in the plane of the board, one coming towards you, one pointing away from you. And then we've got variations on those. But we'll come back to that here in just a minute. How do you do it? Well, there's a series of steps that you can follow. It's not all that involved. And there's a few things that you want to be able to do. The first is always the same. It's making sure you do your bookkeeping. Make sure you can count up the number of valence electrons involved. Then we're going to do something called draw the Lewis structure. This is less complex than you would think. And then from that we're going to get something called the Vsepr structure. Now I'll talk to you about what that means when we get to it. Alright, so let's use, as an example, let's use methane. Alright, natural gas, the stuff that heats your house. Alright, maybe that heats your house unless you have propane. Valence electrons. Alright, so what we're asking ourselves is, how many valence electrons do we have in this molecule? Well, to do that, all you do is add up all the valence electrons for each atom. Carbon's in group 4, therefore 4 valence electrons. Hydrogen's in group 1, 1 each, and there's 4 of them. That gives us a total of 8 valence electrons. Now what that means is when we draw out our structure, we want to make sure that we've used all 8. We can't use less or more. I can't use 9 valence electrons and then just say, you know what, let's just pretend the instructor doesn't know he's a dumbass. Anyway, and you can't have 6 electrons either. You have to use 8. If you've used less or more, then it means you're screwed up. It means you are incorrect. Right. Now, Lewis structure. The way we can do this is, usually what you look for is which atom is central, which is the one that all the other atoms are going to be around. All right? And the simplest way to do it is to say which atom is, so there's two ways to do it. Which atom is the least electronegative, or which atom forms the most bonds. The electronegativity argument works in most cases, just not this one. Beryllium is less electronegative than chlorine, carbon's less electronegative than oxygen, and actually it doesn't work here. So the way to look at it that does work in every case is to look how many bonds does each atom want to form. Well, to do that we look at valence electrons. When we look at carbon, carbon has 4 valence electrons. It wants to form 4 bonds. Hydrogen has 1 valence electron. It only wants to form 1. Therefore, carbon is the central atom. When you look at ammonia, nitrogen has 5 valence electrons. Therefore, it wants to form 1, 2, 3 bonds. Hydrogen only wants to form 1, so nitrogen is central. When you do carbon and oxygen, we already know carbon wants to form 4. Oxygen has 6 valence electrons. It wants to form 2. All right. Beryllium wants to form 2 bonds. It's got 2 valence electrons. Chlorine's got 7 and wants to form 1 bond. Therefore, you always go for the central atom that forms the most bonds. Hydrogen, by definition, is always going to go on the outside because it can only form 1 bond. So for methane, our CH4 has a structure where carbon's central. And then you've got 4 hydrogens around it. We know that because the problem tells us we have 4 hydrogens. Right? So what I'm going to do is I'm going to put the 4 hydrogens around here. I don't know what happened there. And then we're going to hook up each of the carbons and hydrogens. All right? And we're going to use a bond. All right? Now sometimes you'll see this representing the bond, because really all it is a set of shared electrons. Personally, I prefer to do this because it actually shows the bonds involved, and when you get to 1152, you're going to need to know how to draw these. What we've done is, we've used all the carbons, we've used all the hydrogens, and have we used up 8 electrons? Well, each bond is 2 electrons, so 2, 4, 6, 8. So we've used all our electrons. So check there, and check there. And after we've done that, what we do is we move on to this. Now, Vsepr, this simply stands for valence shell electron pair repulsion, and it's a technical way of saying electrons repel each other. Therefore, they want to be as far apart as possible from each other. So whether your electrons are in bonds or lone pairs, this Lewis structure is not usually the most accurate representation, because if you look at the structure, it looks like it's just flat. Carbon with bonds going 90 degrees to each other. All right. Now the fact is, these hydrogens, these carbon-hydrogen bonds and the electrons in them want to be as far apart from each other as possible. This is not the optimal way to do it. The optimal way to do it is what's shown here. Hang on a minute, what am I doing? Here we had our bond angles of 90 degrees. We want those bond angles to be as big as possible because that maximizes distance from each bond to each other. The optimal way is to get a bond angle of 109 degrees by drawing something that's tetrahedral. And that's what this guy is here. This means the central atom with the 4 atoms around it arranged as far apart from each other as possible. This is physically the furthest apart these 4 groups can be. So therefore, what that means is the Vsepr structure for methane is, if I ask you to draw it, it essentially looks like this. You've got 2 bonds in the plane of the board. And I'll show you guys models of this in class. You've got 1 bond coming towards you, and then 1 bond, 1 bond coming away from you. And that is tetrahedral. And that's how you draw structures out. And depending on what you're given, you can come up with a variety of different structures. Alright, so rather than me just talking you through these, I want to do a couple of other examples just to make sure that you guys can see what the hell is going on. So we did, bollocks. So we didn't do bollocks, we just did this. So we're going to go on to beryllium chloride, BeCl2. So what we're going to do is we're going to do exactly the same as we just did. The first thing we do is say, well, valence electrons. Well, beryllium's in group 2. There's 1 beryllium. Chlorine is in group 7, and there's 2 of them. 2 plus 14 is 16. Therefore, if I know that I have the right structure if I draw out a structure that uses 16 valence electrons. Now we said before, beryllium forms 2 bonds. Now we know that because it's got 2 valence electrons, and each unpaired valence electron is a place to form a bond. And chlorine has 7 valence electrons, it's in group 7. Notice that it only has 1 place. Therefore, the beryllium is central. And hopefully it makes sense to you that then the chlorines are either side of the beryllium. And of course, the simple way to hook these two up is just to put single bonds here. Right? But this is only used 4 electrons, 2 here and 2 here. The other thing we have to remember when drawing these structures out is something called the Octet Rule. And that is that all atoms, with a few exceptions, want to have 8 electrons around them. When we look at methane here, look at the carbon. It's sharing electrons from each of the hydrogens. Carbon has its original 4, and the carbon is sharing 4 electrons from each hydrogen, from 1 from each hydrogen, giving a total of 4. Therefore, there's 8 electrons around the carbon. All right? So the only elements that don't need to follow this are those that are too small to do so. And there's only really 3 that you guys need to know about: hydrogen, beryllium, and boron. All right? Hydrogen has 1 valence electron. It can only form 1 bond. It can only have 2 electrons around it. Beryllium has 2 electrons around it. It can only form 2 bonds. It can only have 4 electrons around it. Boron has 3 valence electrons. It can only have 3 bonds around it. It can only have 6 electrons around it. Everything else can adhere to the Octet Rule. These guys get to disobey it. So, when we go here, we say, well, beryllium can only form 2 bonds, and it's already forming its 2 bonds. It can only have 4 electrons around itself, and it's got those. And so we've used 4 electrons, which means we've got 12 left to use. Now, chlorine wants to have 8 electrons around it, and each of the chlorines has 2. So we're going to fill electrons in pairs. These are called lone pairs, or poise pairs. There we go. And if you do that and you count up all the electrons, oh, you did. That should be 2 electrons. Bloody software. Let me try that again. And you count up all the electrons: 2, 4, 6, 8, 10, 12, 14, 16. You've used all the electrons. So now that's the Lewis structure. So when we go to what the Vsepr structure is, well, we ask ourselves, how many directions are electrons going in around that central atom? And when I say directions, I mean that includes bonds and lone pairs. But we're talking about around the central atom. So I'm hoping everybody can see the electrons are going in over here and over here. That's 2 directions. When you have electrons going in 2 different directions around the central atom, it makes sense that the furthest apart they can be is 180 degrees to each other, which gives the shape as being linear. It's where this bond angle is 180 degrees. All right. So this is linear. The bond angle, as we just said, is 180 degrees. And that's it. That's the correct structure, the correct geometry for BeCl2. Now, let's do carbon dioxide, okay? Carbon dioxide. So we've got CO2. Carbon makes 4 bonds, oxygen makes 2, so we know we're going to have this. Now remember what we said before. We have to look at the valence electrons, right? So carbon wants to make 4 bonds. Oxygen ideally has 6 valence electrons, therefore wants to make 2 bonds. And we want to try and do that if we can. All right? So how can we come up with a structure that gives carbon all its 4 bonds and oxygen its 2 bonds? All right? Now when we look at valence electrons, carbon we said was in group 4, oxygen is in group 6, and there's 2 of those. And what do you know? We have 12, actually we have 16 valence electrons here. All right? So let's see if we can figure this out. In the last structure we had 16 valence electrons too. So let's see what we can do here. So what we're going to do is we're going to do exactly what we did before. We're going to put lone pairs, so we're going to put bonds between these 2. And then what I'm going to do is just exactly what we did before. in the last structure and put these lone pairs here. And now what I'm going to ask you guys is a little bit of error analysis. Can you see anything wrong with this? Well, I'm hoping you guys can see actually there's two things wrong with it. We've used the right number of electrons, but carbon does not have its required number of bonds. It doesn't have an octet. Oxygen has an octet, but it doesn't have its correct number of bonds, which means we've done something wrong. What can we do to give oxygen its 2 bonds that it wants and carbon its 4 bonds that it wants? Well, that's where the concept of something other than single bonds comes into play, specifically double bonds. If a single bond is 2 electrons, a double bond is 4 electrons, right? So that means then if we have these 2 double bonds around the carbon, can you guys see we've got 4 bonds around the carbon, 8 electrons, so the carbon is happy. And if we've used 4 bonds, we've used 2, 4, 6, 8 electrons, which means we've got 8 more to use. So we've got to go, after we've done the central atom, we've got to go to the outer atom. Oxygen has its two bonds, but does it have 8 electrons around it? Well, no, it doesn't. It's got 4 electrons around it from the double bond. We need to put the lone pairs on the oxygen. Notice we had them before, but we had more lone pairs before. Now we have less. And if you count up the lone pairs, if you count up the electrons, 2, 4, 6, 8, 2, 4, 6, 8. You've used 16 electrons. The oxygen has its required number of bonds. The carbon has its required number of bonds. Everything has 8 electrons. Everything is happy. So, the last question then is, what would be the actual geometry? Well, if you see these 2 bonds are going, there are 2 directions electrons are going in around the carbon, this way and this way. Therefore, the geometry is going to be just the same as it was here. Therefore, CO2 is also going to be linear, with a bond angle of 180 degrees. All right. Now, the last one here is ammonia. You guys know what ammonia is? It's a cleaning product. It kind of stinks. NH3. So the first thing we're going to do is exactly what we did before. All right. Now, before I do that, okay, let's see. Let's look at valence electrons again. Nitrogen is in group 5. Hydrogen is in group 1. This gives us 8 valence electrons that we have to play with. Because nitrogen's in group 5, as we've previously said, it forms 3 bonds. Hydrogen only forms 1, so therefore our structure is going to look something like this, where we've got nitrogen with 3 hydrogens around it. We do exactly what we did before. We stick the bonds on. Now, hydrogen only wants to form 1 bond, so each hydrogen is happy. Nitrogen wants to form 3 bonds, but it also needs its octet of electrons. How many electrons have we used so far? Well, we've used 1, 2, 3 bonds, so 6 electrons, meaning we need to place 2 more electrons, and we place them as a lone pair there on the nitrogen. Okay? Now, this one is a little bit different to this one. This is tetrahedral. There are 4 groups going around the carbon, but can you see here that we've got all 4 of those groups are actually bonds. When we look at this guy, are all 4 of these groups bonds? Well, of course, no, they're not. There are 4 groups, but one of them is a lone pair. Now, in terms of the directions of electrons, we still count these together. So the electrons are going in 4 different directions. All right. So that would first tell us that maybe the structure is tetrahedral. However, it's not quite that, because this lone pair doesn't really like the others and pushes them away. It's repulsive. Well, that doesn't sound very good. It pushes on the bonds so much that its geometry changes just a little bit. Let me show you what I mean by looking at the table. All right. So when you have 4 bonds around your central atom and no lone pairs, that gives you tetrahedral. When you have 3 bonds around your atom and 1 lone pair, although the bond angle is about the same, the name of the geometry is slightly different, and I'll show you why. When you come up with the name, all you're coming up with is the atoms and the bonds, all right? So if I just draw this out, in exactly the same way that we did before, and say, well, I'm going to put my central atom here, there's my nitrogen. I'm going to draw the 2 bonds in the plane of the board, the 1 bond coming towards us, and then the 1 bond going away. Oh, you bloody thing. I'm going to put my hydrogens, it doesn't really matter where you put the hydrogens, I'm just going to choose to put them all down here. Because down here we have these, and then up here, this is an actual bond, this is our lone pair. When you come up with the name of the geometry, you're actually not taking into account the lone pair, just the bonds. So that means there's only bonds going in 3 different directions. And what we have here is essentially a shape. If you cover this bit up, it will look like a pyramid, but it's a pyramid with a triangular base. This is called trigonal pyramid, or trigonal pyramid, at least I think that's what the book calls it. Trigonal pyramid, there we go. And the reason why it's that way is because this structure here is not actually a bond at all, as we said, but just a lone pair. It's still there, it's just not accounted for in the geometry, because geometry only takes into account bonds. So, essentially, that is how you design structure. That's how you come up with Vsepr structures from formulas like this. Now, the last thing I want to do, hang on with me before we finish, is about polarity. Overall polarity. Let's look at methane to begin with. There's a quick and dirty way to do this, which I'm going to give you. All right. Imagine a molecule like CH4. Whether it's trigonal planar or linear or tetrahedral, it doesn't matter. If all the atoms coming off the central atom are all the same, then any dipoles or charge separations in that molecule will all cancel each other out. What I mean by that is, if you remember before when we talked about drawing out polarity of bonds, and we showed something like this, we also showed something like this with the arrow pointing towards the least the most electronegative element. I don't know if I got those mixed up or not. Anyway, whatever. When you take something like this, I'm going to draw out something tetrahedral. And I'm going to put on these bonds, H, 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 and H. And you put on all those dipole arrows. This is a dipole arrow. It doesn't matter whether the dipole arrows all point out or point in. For the purposes of simplicity, I'm just going to draw them pointing out. If I drew them pointing in, it would be exactly the same thing. The point is that all these dipole arrows essentially cancel each other out. All right. Now, let me see if I can find something that's easier to explain that with. All right. Let's say we have a molecule that we showed to be trigonal planar. So let's say we've got X, Y, Y, and Y. And we're found to have 3 groups around the central atom, and so the geometry would be trigonal planar like this. If we were to look at these dipoles, this one going up would cancel out these 2 going down. The overall result would mean 0 overall dipole. And that's the case whether you've got 2 groups, 3 groups, or 4 groups around the central atom. If all these guys are the same, they all cancel out. So that this molecule overall is non-polar. And the only time this changes is when one of these atoms changes or one of them is replaced by a lone pair. Because then they won't cancel each other out. So, for example, we'd seen that methane was non-polar. All right, we just saw that. Now, beryllium chloride. All right, if we just look at what we did here, you've got chlorine's more electronegative than beryllium. So you've got 1 dipole arrow this way, 1 dipole arrow this way. Now, I'm sure you can see this is linear. These 2 are exactly opposite to each other, and they're also same magnitude because chlorine's the same. Therefore, what would these 2 arrows do to each other? Of course, they cancel each other out, meaning the overall dipole is 0. The dipoles would cancel. So notice for the beryllium chloride, there's no lone pairs on the central atom. There's no lone pairs on the central atom of methane. Both of those all cancel each other out, so they're both non-polar. CO2. If we go to CO2, Same thing, oxygen's more electronegative than carbon, therefore this is linear. These two dipoles exactly cancel each other out, meaning the polarity overall is 0. There's no lone pairs on the central carbon there. But if we go to ammonia and look at this guy, nitrogen is actually more electronegative than hydrogen. So I'm just going to show an arrow like this for this guy, an arrow like this for this guy, and an arrow like this for this guy. Now it doesn't matter whether these point up or down, but if you notice, these arrows all point up. Is there anything up here pointing down, cancelling them out? Well, of course the answer is no, because that's a lone pair and not a bond. If you look at them, what the overall dipole is then, the overall dipole results in one that points up, because that arrow, and that arrow sort of add each other up to give you something that's overall polar. So even though in CO2 you have bonds that are polar, if you calculate the electronegativity difference, these are indeed polar, they cancel each other out. These don't because of the lone pair. So the key is, does your central atom have a lone pair on it or not? If it does, the dipoles won't cancel. If it doesn't, dipoles cancel. Dipoles cancel, and dipoles cancel. Alright, that was a bunch, but hopefully it makes some sense. Alright, thank you.